This is a famous line integral because it's going to show us that even though we are integrating it over a closed curve C, here we have the unit circle, we cannot use the Green's theorem. In fact, we cannot use the fundamental theorem of line integral either. I will show you both of them and see what we will get, and I'll show you how to actually do it with parametrization and get the correct answer. So let's have a look. First, when we have a line integral over some curve C, if it's closed, and here let's say we have p dx plus q dy, then Green's theorem says change that to a double integral over the region. Here we have the unit circle. Inside you do partial of q with respect to x minus partial of p with respect to y, and then dA. So let's go ahead and get our partial derivatives. Here is the p, which is negative y over x squared plus y squared. We will have to differentiate this with respect to y, so we get this. Okay, we get partial of p with respect to y. We will have to use the quotient rule. So let's just go ahead and do that. X squared plus y squared, go ahead and square the bottom like this. Put the bottom to the top. Multiply by the derivative of the top function with respect to y, which we need the -1. And then minus the top function, which is negative y. So that will turn that into a positive. And then multiply by the derivative of the bottom with respect to y. And we need 2y. Now simplify the top. This is going to be negative x squared, and then negative y squared, and then plus 2y squared. That will be plus y squared, and then the bottom. Then do the same thing for q. Here we have x over x squared plus y squared. Take the partial with respect to x, and we get partial of q with respect to x. Again, do the quotient rule. So square the bottom, and then put the bottom to the top. Multiply by the derivative of the top function with respect to x, so we get 1. Minus the top function, which is x, times the derivative of the bottom with respect to x, so we need 2x. Okay, let's see. You're going to see something kind of strange. X squared minus 2x squared, so that's negative x squared, plus y squared. Oh my goodness, this and that are the same. So if you just go ahead and use the Green's theorem, change this into a double integral, I don't even have to worry about what goes here and here, because this minus that, we will get 0. And no matter what these are, integrating this 0 thing, we will just end up with 0. But as I told you guys in the beginning of the video, this is actually not the correct answer. I'm just going to write it down right here now. If you use Green's theorem, we get the answer 0, but this is not correct. Okay, let's try to see if we can use the fundamental theorem of line integral. So earlier we saw that the partial derivatives are equal, so in fact we can actually find a function f of xy such that if we differentiate this with respect to x, we get this. If we differentiate this with respect to y, we get that. Just to save time for this video, I will tell you the function is inverse tangent of y over x. And I'm going to verify with you guys right here real quick. If we take the partial with respect to x, take the derivative with the inverse tangent, we get 1 over 1 plus whatever this is, and then you square that, and then you multiply by the derivative inside. This is yx to the -1. Take the derivative with respect to x, put the -1 to the front, this stays, subtract 1, so that's what we have. And then I'm going to fix this a little bit. Negative y to the top, over this on the bottom, and then square that, so we get y squared over x squared. Distribute the x squared, we get negative y over x squared plus y squared, which is this right here. Very nice. And then if we take the partial with respect to y. Here's still 1 over 1 plus y over x squared. This time we multiply by the derivative of this with respect to y, and that will give us 1. So we still need x to a negative 1. I'm just going to write it down like this. So now I'm going to do the following. For this part right here, this is like this, 1 over 1 plus y squared, depends on how you want to simplify it. Like this, right? And then the x to a negative 1, I'll put it right here like this. And then I'm also going to multiply the top and bottom by x squared. And then distribute this. So this times that, we get the x squared plus y squared. And then this and that cancel, so we get x on the top. So that's just the algebra part, but this matches that. So what that means is that if you take the total derivative of this, you will get that. So this is the total differential of that. And then when you integrate the total differential, you just get the function back. That's the idea. So I'm going to just look at this right here as inverse tangent of y over x. But now we need the numbers, right? What numbers do we plug in? If you look at the unit circle, right here, let's say this is our starting. It's just 1, 0. You go one loop, you end up with 1 over 1, 0 as well. So 1, 0, 1, 0. When you plug in, guess what? You just get 0. In fact, if you plug in 0, that's also 0. So it's very 0 for this one. So you totally get 0, right? Fundamental theorem of line integrals, it also gives you 0. But again, this is not the correct answer. It's not. So how exactly do we do it though? Let's have a look. So lastly, I will show you guys what if we use parametrization to solve this line integral. And because we have a unit circle, we'll just do x equals cosine t, y equals sine t. And notice x squared plus y squared will give us 1. And then because we are going in one loop, so we know t will go from 0 to 2 pi. Now take this integral to the t world. Negative y is sine t. And then x squared plus y squared is 1. dx, take the derivative of that, we get negative sine t dt. So this is the dx part. Continue, plus x is cosine t. On the bottom is 1. And then dy, look at that, take the derivative, we get cosine t dt. And this is the dy part. We are in the t world, so we go from 0 to 2 pi. Now have a look. This times this is just what? Positive sine squared t. And now I'll put the dt all the way at the end. And then this times this is cosine squared t. This is so nice, isn't it? Because this right here is just equal to 1. So we are just integrating 1 in the t world, going from 0 to 2 pi, and the answer is just 2 pi. In fact, this is the correct answer, not 0, not 0. Now, let's talk about why not. How come the Green's theorem and also the fundamental theorem of line integrals, they didn't apply? Well, it's because if you look at this region here, we actually have a bad point. That point is the origin, because that is 0, 0. When x and y are both equal to 0, if you look at the bottom, what do we get? We get 0 on the bottom, which is very, very bad, right? So we have to be super careful if we have any bad number on the region that we are trying to integrate. For these theorems cannot apply. This idea is very similar to when we were trying to do an improper integral back in Cal 2. So have a look. If we have the improper integral going from -2 to 1, 1 over x squared, can we just use the fundamental theorem of calculus, get an antiderivative of this, plug in 1, plug in -2 and subtract? No, we cannot do that. If you did that, you end up with a fake answer, a wrong answer. And notice that it's just that we have a vertical asymptote at x equals 0, because 0 is on this interval. It's bad. And now you might be wondering, if we have a bad number on the region that we're trying to integrate, how come we can still end up with a nice answer? Well, some improper integral back in 条2, they also have nice answers. For example, if you try integrating 1 to 10, 1 over the cube root of x minus 2, we can see that this right here is bad at x equals 2, and that is on the interval. But in fact, you can actually end up with a nice answer, and I'm going to leave that to you. That idea, it's the same right here. Even though we have 0, 0, it's bad, but you can actually work it out. You just have to use the traditional way. Lastly, let me just mention that this vector field is famous. It's called the Vortex vector field, which is defined to be negative y over x squared plus y squared, comma, x over x squared plus y squared. So you guys can look that up, and yeah, an example where you really have to be careful when you use the green theorem and also the fundamental theorem of line integral. Hopefully this really helps. If you have any questions, feel free to leave a comment down below and let me know. That's it.